Welcome students, I'm Rebecca Weaver and this is your Calculus 3 course. We're going to begin with Chapter 12, talking about vectors. We're just going to start at the ground zero, explaining what a vector is. A vector is something with both magnitude and direction, meaning it has a length and it is going in some sort of direction, whether that be north, south, northeast, might have an angle associated with it. If we were talking about something that was going northeast, we will say that two vectors are equal if they have the same magnitude and direction. So same magnitudes, same length, and the same direction. And they can be placed at different spots on the plane. A scalar is just a magnitude without direction. We can look down here at this to see an example of this. If we have this vector v, the number 3 would be a scalar, and saying 3 times v would just mean 3 of those vectors v. So 3 of those vectors in length, but going in the same direction. Notice how it doesn't change the direction. The zero vector we might want to mention has no length and no direction, has virtually the same properties as zero, just as you would common sense wise think that it would. Here are a few examples of vectors in real life and things that you'll have to deal with in your physics classes or your engineering classes. Just looking at some of the notation and how we would denote these. The vector PQ looks like this, starting at P going to Q, and we would say, because these can be anywhere in the plane, that's basically just the vector U. So I'll just write that it's U. Q to P. Oh, that's going the other way. Now, for the purpose of denoting that this is a vector, I am going to, because I can't write in bold, I'm just going to put an arrow over the top of U so that you know it's not just a scalar, but it is a vector. And next I am doing Q to P, which goes in this direction. And this looks a lot like U, but it's exactly backwards, and I will represent that by negative U. Q to R. Let me get rid of that one. Oops, never mind. Okay, Q to R looks like this. So Q to R is 2 of these V's. So I'm going to write that as 2 these vector V's. Then R to S. I'll just do this in a different color. R to S would be 3 of those U's, but in the other direction. So I'm going to write negative 3U. And I'm writing that vector over the top to denote that it's a vector because I can't really write in bold. And I will expect you to do the same on your show your work problems. Next, I'm wanting to write the vector OP in terms of V and W. So let me see what OP is. If I go from O to P, that's going to be 1, 2, 3 of these V's. So OP is 3 of those V's, and then 1, 2 of those W's. That's really all there is to this sort of thing. I'm going to do O to Q next. So O to Q is going to be 1, 2, 3 of the V's again, plus, oh, looks like I gotta go the other direction. I should have just written minus just 1 of those W's. Next is Q to R. Q to R is Q to R. I'm going to go one of those V's and two of those W's. And that is representing those vectors in terms of V and W. Just going over a few of the basic definitions here. A position vector has to have its tail at the origin and goes off in some direction unless it's, of course, the zero vector. This P can be written, it's a point here, but OP is a vector and it happens to be the position vector and can be written as, because it is the position vector, it can be written as -3, 4. If we want to know the magnitude of this position vector, what we would have to do, in other words, you want to know the length of this line, I would compute this right here. So I'm going to do the magnitude of OP. I'm just filling into just the regular distance formula, which is the square root of the difference of the x's and the difference of the y's. And this would be, right, that distance when you do the computation is 5. So that's the magnitude of vector OP. Now for PQ, in order to get that vector representation, what I'm going to have to do is this right here. Notice that it is the second point, because Q is the x2, so it's the second point minus the first point. So I'm just going to do 6 minus a -3, which would be a 9. And then it is 5 minus 4, which would be a 1. In order to get the magnitude of that vector, I can use this distance formula, or I can, because I now have this in terms of just a regular vector format, and I could have done it on this one as well, I'm just going to take the square root of each of those values squared. Doing the arithmetic for that, I get the square root of 82. And I'm sure that would simplify, but I'm just going to leave it as such. Well, maybe it doesn't. 41, no, okay, it doesn't, so it's good. All right. We have definition here of if we add two vectors, as long as you have them written in standard form, which is what the U and the V represent, then you can just add those vectors. Same with subtraction, you just subtract them and then multiplication by a scalar. So 4a asks me for the magnitude of U plus V. So the first thing I need to do is get U plus V, and that would be adding the x components. That would be 1, 2 and 3 or 5. Getting the magnitude of this is just using that distance formula, but since it's in standard form, I can just say 1 squared plus 5 squared, which would then be square root of 26. The B part, 2 U's minus 3 those V's, so 2 of those U's, U minus 3V, 2 of those U's would be -2, 4 minus 3 times V, be 6 and a 9. Just adding each of those components, I get the vector. That would be -2 minus 6 would be -8. 4 minus 9 would be -5. And then the C part, I'm supposed to find two vectors half as long as U. So let me just do this. Half as long as U. 1/2 U. Let me get my little arrows over the top of these things because I got a little sloppy. And okay, half as long as U, that would be -1/2 and 1. And then I need one that's parallel, so I'm just going to go the other direction because it would still be parallel. This would be 1/2 and -1. That's it for that one. unit vectors have a length of 1. So they gave us that we can say that I is going to be the unit vector that goes in the x direction, and j will be the unit vector that goes in the y direction, and this will give us a easy way to manipulate some notation here. The first thing they want me to do is find PQ. So for 5a, PQ, remember doing what we did before, it's going to be the second one, 6 minus the 1, that's a 5. 10 minus a minus 2, that's a 12. I can write this as 5i plus 12j, where these are both my unit vectors. And we can also write those with little hats instead of using this vector, and it's a lot easier to write 5i hat plus 12j hat, and that just means it is that unit vector multiplied in each of those cases. So I need for PQ to be represented as this unit vector because we want one that's parallel to that. So I'm going to need to know the magnitude of PQ, and the magnitude of PQ, I'm going to do that algebra, would be 13. So right here, what this lets us know is that since this vector has a length of 13, I can represent this as a unit vector by writing it as 5 over 13 I hat plus 12 over 13 j hat, and all you're doing is just dividing out that magnitude. Or I can write it the other one, because they want two of them, is just the negative version of that. Both of these are unit vectors, which means they have a length of 1. So if I want two vectors of length 2, so these guys have a length of 1, I'll just multiply each of those by 2, and then I'll have what I was looking for. So let me do that. Okay, so I went ahead and did that arithmetic, and that's all they're looking for there. Basically, these problems aren't necessarily hard, they're just conceptual and wanting to get the definitions down pat and your notation in writing these things correct. This is just a summarization of the different properties that you can use with vectors and that we've gone over so far. We can extend, we can say that it doesn't matter what order we add our vectors in. I can, it follows the associative property, so it doesn't matter which one I associate or add in whichever order. If you add to the 0 vector, you still get itself. You add the opposite, you'll get 0, and so forth. So these are just summarizations of things that follow from what we have done so far. Recalling from trig, a couple of basic identities. Sine is the opposite over the hypotenuse, so sine is the y component, which would be, so the sine of theta is the y component over the hypotenuse, which is your f. Just solving that for f sub y, you'll get what's over here, and same thing for cosine. You'll just replace that with the f vectors. So I've written all of this out for you. You can choose to write the vector over here or not. It really doesn't matter, but when you've written that y, you're automatically stating the direction, so you'll get both the magnitude and the direction from this, because I know that if it's f sub x, it's in the x direction. Don't really need any of this stuff that I've learned so far in this chapter to be able to do this problem. If you've taken a basic physics class, you're just finding the x and y component, or even trig class, you've done this. So I'm just going to write that down for you. Okay, so I've cleaned up my notation just a little bit here for you, and then plugged in for my algebra, and I need that force vector F. I now know both the x and the y component. So writing them in proper notation, it would look like, whoops, if I can write a 3 and a 10, and there it is written in beautiful proper notation. In this one, we're looking at some sort of something being suspended by a chain. we're going to assume that the force 1 equals force 2, and we know that force 3, the magnitude of force 3 is that 400 pounds. If I were to describe force 3 in terms of vectors, that would be, let's see, his x component, he doesn't really have an x component, he's just pulling straight down. So written in standard notation with his tail at the origin, this was what that one would look like. The fact that force 1 and force 2 are equal is going to become important to us here in just a minute. We'll say this is fx and this is fy. Likewise on the other side, this is f1x, f2. f1x, I know that we have that angle of 60 degrees, which means that f1x is going to be equal to that f1 times magnitude times, and then the x is the adjacent, so that's cosine of that 60 degrees, and then f2x is going to be f2 cosine 60, and then the f1y is going to be that sine. Now, concerning myself with direction, force 1 is acting to the right and up, so both of those are positive. Force 2 is acting to the left on the x, so you're going to need a negative on you in order to get that correct. So let's write down what f1 looks like. We need that x component, which is f1 cosine 60. I'm going to go ahead and write all of these down. I know that the end result is the fact that this weight is being suspended. So f1, that vector, plus f2 is going to equal f3. f3 happens to be 0 minus 400. I can now use vector addition to say that these two guys right here are going to add up to be 0, and these two guys right here are going to add up to be that 400. And the reason for that is the fact that it's not moving, so I know that if I were to add them all up, it's not moving, so it equals 0, and so then I just move this over to the side, and that's where that negative came in, so I know that this thing equals that 400. These two guys add up to be 0, so I'll do the algebra of that. Okay, when I plug all of that in, I'll get the 400 over 2 times the square root of 3 over 2, and then that would give me 231 pounds, which is what each of them would need to, each chain would need to hold up in order to hold that 400 pounds with these angles. As such, you change the angles and then you'll change how much weight each one will have to hold up, because that was a factor here. And then the x components aren't doing anything for this problem. And watch your negatives. As you can see, I was having to make sure I got my negatives all in there correctly, because to add up to 0 I would say it and then I got to make sure that I write it down correctly as well. Alright, good luck, and if you need any help, you need to see me at the collaborative.